In this video, we will look at a very specific application of integration, and that is to find the mass and center of mass given a density using double integrals. So the examples that are given in the book often involve what is called a lamina, and our definition is a lamina is a thin plate, usually made out of some sort of metal. And we're going to describe a lamina by the region R in the plane that it covers. And then this lamina will have a density function, mass per unit area, at a point xy in R. And that will be given by the function rho of xy. So once we have a mass density in a region in the plane R, then if we want to find the total mass, we can integrate that density. So the mass of a lamina is the double integral over that region R dm, or the double integral over that region R of our density rho of xy dA. So in this sense, we're saying a little bit of mass, dm, is the density rho of xy times a little bit of area. So just like in single variable calculus, if we integrate the density, then we're going to get mass. Now, once we have a way to calculate mass, then we can calculate the center of mass. So the coordinates, which I will label as x bar and y bar, of the centroid, which is another name for center of mass, of a lamina are defined to be x bar, which is 1 over m, 1 over the mass, times the double integral over r, x times rho of xy dA. So here we're going to integrate x times the density function and then divide that by m, and that's going to be our x coordinate of the center of mass. The y coordinate will be 1 over m, double integral over our region R of y rho of xy dA. And that will be the y coordinate of the center of mass. And so here we're thinking about the center of mass, or centroid, as the point of the lamina where it would balance horizontally if it was placed on the point of something like an ice pick. Okay, this is the point where this thin metal plate that has some sort of area density, okay, would balance perfectly. And then I want to bring up a principle of symmetry here that says if the plane region R is symmetric with respect to some line L, the centroid, or center of mass, of that region R will lie on L. And this is something that we're going to see in the example. So our example is find the mass and centroid, or center of mass, of the region bounded by y equals 0 and y equals 4 minus x squared. With, in this case, we're just going to have a density of 1. So what we have is this thin metal plate. It has a density. We're going to say it's 1. Okay, it's bounded above by y equals 4 minus x squared. And then, so that parabola, it's bounded below by y equals 0. So we want to find the mass of this shape. And so what we're going to do to find the mass is we're going to integrate the density. So the mass is going to be a double integral of the function 1. And we're going to integrate that, let's say, dy dx. Now, to describe the area of this region, we can integrate from y equals 0 up to y equals 4 minus x squared. And then the x's would then have to go from -2 to 2. I'm going to make a quick simplification before we get started, and I'm going to recognize that this metal plate is symmetric, and so I could do twice the integral from 0 to 2 if I would like to find the area of that metal plate. We can also recognize that this works because 1, the integrand, is an even function. Now, if I integrate dy, then I'm just going to get y. And so the inner integral is just going to be 4 minus x squared. Now I'm just left with the outer integral. So here I'm going to do 2 times, and then the antiderivative of 4 is 4x, and the antiderivative of x squared is 1/3 x cubed. Oh, and I'm going to evaluate that between 0 and 2. So here I'm going to get 2 times 4 times 2 minus 8/3. Okay, so this is going to be 2 times 8 minus 8/3. Now, 8 minus 8/3, that's going to be 24/3 minus 8/3. So that's 16/3, and I multiply that by 2, and I'm going to get 32/3. Okay, so the mass of this plate, okay, which is in this case the same as the area because the density is 1, the mass is going to be 32/3. Okay, now what's left? Well, I want to find the x-coordinate of the center of mass. So the x-coordinate of the center of mass is going to be 1 over the mass, 3 over 32. And then I want to integrate from -2 to 2. And then I'm going to integrate from 0 to 4 minus x squared, x dy dx. Now, this x, or this inner integral dy, does not depend on x, so I can kind of bring the x out there. So I'm going to get 3 over 32, the integral from -2 to 2, and I'm going to get x times the integral from 0 to 4 minus x squared of dy. Again, we see that that's just going to be 4 minus x squared like it was before. I'm going to integrate that dx. Now, inside this integral, I see x times 4 minus x squared. So I have an odd function times an even function. So this is going to be an odd function. I'm integrating an odd function on a symmetric interval from -2 to 2. And you should remember from calculus 2 that if you integrate an odd function over a symmetric interval, that integral must be 0. So in fact, the center of mass, the x-coordinate, is 0. And this makes sense because our plane is symmetric about the y-axis, or x equals 0. And so we expect the center of mass to lie along that y-axis. That is that symmetry principle that I mentioned before. So it's symmetric about a line. That line is the line x equals 0, or the y-axis. And so we expect the centroid to be on that line. So the x-coordinate is 0. Now let's look at the y-coordinate. Okay, the y-coordinate is going to be 1 over the mass, so 3 over 32, okay, times the double integral from -2 to 2, and then the integral from 0 to 4 minus x squared. And now we're going to integrate y times the density, which is 1, dy dx. So this is going to be 3 over 32 times the integral from -2 to 2 of 1/2 y squared, evaluated between 0 and 4 minus x squared. That is all integrated dx. So we're going to get 3 over 32. And then we'll have the integral from -2 to 2 of 1/2 times 4 minus x squared squared. And then when we substitute in y equals 0, we're going to get 0. Okay, so I'm going to do two things to simplify here. The first thing I'm going to do is, again, I'm going to recognize that I have inside here an even function, 4 minus x squared, quantity squared. So because that is an even function and I have a symmetric interval, I can integrate double. Okay, so getting rid of the 1/2, integrate from 0 to 2. So here I have an even function. Integrate from 0 to 2, 4 minus x squared squared, and I'm going to go ahead and square that out. So that's going to be 16 minus 8x squared plus x to the 4th. Integrating that dx. Well, this is going to be 3 over 32 times 16x minus 8/3 x cubed plus 1/5 x to the 5th. I'm going to need to evaluate that from 0 to 2. So finally, we're going to get 3 over 32. Okay, now I'm going to substitute in 2. So I'm going to get 32 minus 8/3 times 2 cubed, which is 8. So that's minus 64/3. And then I'm going to get plus, and then 2 to the 5th is 32. So 32/5. Now, if we work all of that out, okay, add those all up, we're going to get 8/5. So the y coordinate is going to be 8/5. So our mass is going to be 32/3, and our centroid, in this case, is going to be 0.8/5. So here, if we're going to mark our centroid, okay, so it's going to be 0 and then 8/5. So it's going to be, if this is 2 and that is 4, then our centroid is going to be somewhere about here. Okay, so it's somewhere between 1 and 2. Okay, and you'll notice right on the lower half we have more area, more mass than we do on kind of the upper half of that plate, and so that's why that center of mass is going to be right there.